Hi, I'm Dylan Chan, a pediatric otolaryngologist and auditory scientist here at UCSF. I recommend that you listen to this talk wearing headphones, as there are some hearing simulations that are best experienced without ambient noise. Please also be aware that I'll be asking you to adjust the volume on your headphones. So we'll be talking today about how we hear. If you have any questions about this material or want to chat at all about hearing or otolaryngology, please feel free to contact me. So let's talk first about what the ear has to do. The job of any sensory system is to take the reality of a physical stimulus, a sound, a sight, or a touch, and turn it into the language of the brain. And so in the case of hearing, the ear needs to take sound, which is an analog signal, and turn it into a binary train of action potentials. So how would you design a system to make this happen? Think about this for a second. Well, the first thing to do is to think about the nature of the input signal and the output signal. And in the case of sound, sound is variations of pressure amplitude over time. And the output that the brain is looking for is the firing rate of a set of neurons arranged in space. So how does the ear do this? How does the ear make this transformation? So the ear takes advantage of a fundamental property of any complex waveform, in that a complex waveform of amplitude over time can also be represented as an array of intensities over a range of frequencies. So think of it this way. When you play a piano is an array of keys at different pitches. And if you play a particular key, you can play it louder or softer at a particular pitch. But when you play all of the notes of a piece of music together, it creates a complex sound. It creates music. And so in this way, a piano takes a series of pitches played at different intensities and turns it into a complex sound or music. What the ear does is the complete opposite of that. It takes a complex sound and deconstructs it into a series of frequencies at different intensities. Now, it turns out a series of intensities at different frequencies is very analogous to a series of rates distributed over space. And that is fundamentally the trick that the ear does. It takes sound, which is a complex waveform of amplitude over time, converts it into an array of intensities distributed by frequency, which is understandable by the brain as an array of neurons firing at different rates interspersed in space. That's what the ear is able to do. It's able to take a complex waveform of sound, deconstruct it into its component frequencies as an array of intensities, and then map that onto the brain. So how does the ear actually do that? So shown here is a diagram of the human ear. We can start with the outer ear, which consists of the auricle, which you can see, and the external auditory canal, which you can see with an otoscope. The outer ear contributes some sound localization cues, but it's just mostly a conduit for the sound vibrations to get further inside. The middle ear consists of the tympanic membrane, or the eardrum, together with three tiny bones of hearing, the malleus, the incus, and the stapes. And the job of the middle ear is also to conduct the sound from the outside to the inside. It does contribute a little bit of frequency filtering, some impedance matching. Most of the pathology that we actually see in otolaryngology relates to the outer and the middle ear. Everything from oral atresia, which is congenital absence of the ear canal, to much more common things like ear infections or fluid behind the eardrum, which can dampen the transmission or conduction of hearing of sound through the middle ear. And collectively, this is all referred to as conductive hearing loss. Because these are all structural, mechanical, and atomic differences, most of these causes of conductive hearing loss are actually surgically managed. Ultimately, the job of the outer and the middle ear is principally to conduct sound from the outside world to the inner ear, and that's where the real magic happens. The inner ear consists primarily of the cochlea, which is this snail-shaped organ here, and the balance system, which we won't talk about today. The cochlea is what actually turns the sound signals into electrical signals, which are then sent through the cochlear nerve, which is part of the 8th cranial nerve complex, to the brain. So this is a histological section of the cochlea that has been sliced along its axis. And if you take a spiral and you slice it down the axis, you will see that you can see each of the turns, so each of these turns here, as it wraps around a core here. And this core is where the cochlear nerve runs. If you zoom in on one of these cochlear turns, then you can see it consists of 3 chambers. Scala vestibuli and scala media are separated by Reissner's membrane, which is acoustically transparent. And scala media and scala tympani are separated by the cochlear partition, which vibrates in response to sound. The cochlear partition consists of the organ of Corti, separated by 2 membranes, the tectorial membrane and the basilar membrane. If you unroll the cochlea, you can see how this sound transmission actually happens. So sound vibrations are picked up by the eardrum, sent by these bones to the cochlea. And the last bone, the stapes, inserts into a window called the oval window. So when the stapes vibrates back and forth, it sends pressure into the fluid-filled cochlea. As this happens, it sets the basilar membrane into up and down motion with pressure released at the round window here. So the basilar membrane is not uniform along its entire length. At the base of the cochlea, close to the stapes, it is very tight and stiff, and at the apex, it's wider and floppier. Because of this variation, the basilar membrane responds maximally, responds best to different frequencies along its entire length. So at the short, stiff base, it responds best to higher frequencies, and at its floppy apex, it responds best to lower frequencies. And the frequency at which the basilar membrane is tuned along its entire length is referred to as the characteristic frequency. So in this way, when a complex sound is delivered to the eardrum and the ossicles and inserted into the cochlea, because the basilar membrane is tuned along its entire length, the basilar membrane actually deconstructs the complex sound into this array of frequencies. And this property, where frequency is distributed in space, is referred to as tonotopicity. And this is really the trick that the ear uses for sound transduction. Now, when you zoom in closer on the organ of Corti, you can see how all of the cells and the micromechanical structure of the cochlea work to make the actual sound transduction happen. So shown here is a close-up of the cochlear partition. The organ of Corti is sandwiched between 2 acellular membranes, the tectorial membrane and the basilar membrane. And the organ of Corti itself is comprised of sensory hair cells in green, surrounded by supporting cells in white. The apical surfaces of the hair cells are bathed in endolymph, which is a very special fluid that is high in potassium. The basolateral surfaces are bathed in perilymph, which is more like regular extracellular fluid or CSF. There's also a large electrical gradient that is maintained across the organ of Corti, and both the special ionic and electrical environment are created by the stria vascularis on the lateral wall of the cochlea. Now, when the basilar membrane and the cochlear partition are set into vibratory motion up and down, you will see that there are these processes called hair bundles at the tops of the hair cells, which are engaged in the tectorial membrane. And so when the cochlear partition moves up and down, this causes a shearing motion between the tectorial membrane and the organ of Corti, which causes the hair bundles to move left and right. This hair bundle, which is shown here in a diagram of an entire hair cell, is a very specialized structure. It looks a little bit different from species to species, but it always consists of a hexagonal array of actin-filled stereocilia arranged from a short row of stereocilia up to a taller row of stereocilia. And if you look at this transmission electron micrograph of stereocilia, you'll see that they are connected by a little link here called a tip link. So when the basilar membrane moves up and down, and that causes left to right displacement of the stereocilia, you'll see that the two stereocilia move relative to each other. And when they move towards the row of taller stereocilia, it pulls on this tip link to open a mechanoelectrical transduction channel. This channel is broadly permeant to many cations, and because there's a lot of potassium in the endolymph, it's primarily potassium with some calcium that enters into the hair cell. When the stereocilia are then vibrated back in the other direction, the tip link relaxes and the mechanoelectrical transduction channel closes. So in this way, when the hair bundle is stimulated towards the taller row of stereocilia, you have an entry of ions into the hair cell. So you have transduction of a sinusoidal mechanical stimulus into a sinusoidal transduction current. Now, because of the electrical properties of the hair cell, when the hair bundle is deflected towards the taller stereocilia, it causes a depolarization of the receptor potential of the hair cell, a sinusoidal component, and then when the hair bundle is deflected in the other direction, a return back down to baseline. This thus results in glutamate release at the hair cell synapse with the spiral ganglion neuron, such that when the hair cell is depolarized, it results in an increase in the firing rate of the auditory nerve. So in this way, a sinusoidal mechanical stimulus is translated into an increase in rate of auditory nerve firing. Now remember when we were talking about the basilar membrane vibrating differently at the base and the apex, and how the frequencies are represented from high frequency down to low frequency. Because there are thousands of hair cells along the basilar membrane, the hair cells are then arranged in a frequency map, and that maps directly onto the array of auditory neurons. So then the auditory neurons are arranged in a tonotopic map from high frequency to low frequency. So in this way, when a complex sound is introduced into the ear, the basilar membrane deconstructs it into its frequencies, and this frequency map is directly translated into a tonotopic map of auditory nerve firing. And this is referred to as place coding. So the frequency of the sound is represented by the place of the neuron along this array. You can also have some temporal coding, which means that the rate of the nerve firing is somehow synchronized to the actual sinusoidal pattern of the sound that is coming in. And there's an ongoing debate right now as to the relative roles of place coding and temporal coding in how we perceive and how our brain understands sound. So shown here is an animation of the entire auditory transduction process. So a sound is introduced into the ear. It sets the tympanic membrane or eardrum into motion. These vibrations are sent through the ossicles to the cochlea. If you unroll the cochlea, you will see the basilar membrane with the low-frequency apex to the bottom right and the high-frequency base to the top left. A low-frequency sound will be represented towards the apex, mid-frequency in the middle, and a high frequency at the base. If you play the sounds together, it'll stimulate all three locations. If you play a more complex sound, this frequency distribution will still be represented. And so the complex sound will be deconstructed along the entire length of the basilar membrane. If you start with a low frequency sound, it will start right at the apex. And as you get higher and higher and higher, the sound will get more and more and more towards the base. This tonotopic organization of frequency and space is roughly maintained as auditory information ascends through the brainstem and up into the brain. Very early on in the brainstem, there is a lot of integration of sound, especially from both ears, which contributes to things like sound localization, to hearing and noise. And the auditory cortex does a lot of processing to help us understand our auditory environment in very fine ways. However, the fundamental job of the peripheral auditory system is to take complex sound and to turn it into a tonotopic organization that our brain can understand. Now, the peripheral auditory system, because it has to function at such high frequencies all the time, is very sensitive to damage. And hair cells in particular are exquisitely active, and they also do not regenerate. And for that reason, the peripheral auditory system and hair cells in particular are very susceptible to different kinds of damage. So we talked previously about conductive hearing loss, where different structural or anatomic differences in the outer or middle ear contribute to a decrease in sound conduction to the inner ear. But actually the most common cause of hearing loss, and one that almost all of us will experience as we age, is sensory neural hearing loss. And sensory neural hearing loss happens principally when hair cells in the cochlea die. And this can happen, as I mentioned, due to age, due to loud noise exposure, but also to many drugs and due to many genetic causes. And when the hair cells die, even though sound is able to get into the cochlea is unable to transduce that sound and stimulate auditory nerves. In a mild or moderate hearing loss, you're still able to hear, but you have to work a lot harder to hear, especially in noisy environments. In babies or young children, this can lead to significant and permanent speech and language delays. And in older adults, it can lead to significant cognitive decline, dementia, and depression. And hearing loss is actually noted by the World Health Organization as one of the most impactful health conditions. A moderate hearing loss is simulated here. It is depicted in this audiogram, the clinical picture of a person's hearing level, where the loudness of sound on the y-axis necessary to be detected at different pitches on the x-axis is presented. In a moderate hearing loss, shown by the red line, you are unable to hear sounds above the line on the chart, birds, refrigerators, but the most significant part is the majority of speech sounds, which are depicted in this dark gray speech banana here. So I will play you a simulation of a moderate hearing loss. If you turn up the volume really loud and you listen very carefully, you might be able to make out the speech.
One cold, rainy day, when my father was a little boy, he met an old alley cat on his street. The cat was very drippy and uncomfortable, so my father said, "Wouldn't you like to come home with me?"
So compare that to the original clip, and be careful. If you turned up the volume really high on your headphones to hear the previous one, this one's going to sound really loud.
One cold, rainy day, when my father was a little boy, he met an old alley cat on his street. The cat was very drippy and uncomfortable, so my father said, "Wouldn't you like to come home with me?"
So in even more severe or profound hearing loss, there are so few hair cells that even if you amplify the sound really, really loud with hearing aids, you would not be able to stimulate the auditory neurons enough for your brain to perceive the sound. In these situations, a cochlear implant can be used to directly stimulate the auditory nerve. And the cochlear implant, which was actually partly developed here at UCSF, is a device that is inserted directly into the cochlea and consists of an array of electrodes that are inserted along this tonotopic axis of the cochlea. What the cochlear implant does is it actually reproduces the job of the ear. It takes a complex sound, the external processor of the cochlear implant deconstructs that sound electronically into a series of firing rates at different frequency channels. Now, the cochlear implant only has about 20-ish channels, but when the high-frequency channel is stimulated, it stimulates that high-frequency nerve, and then the same for a middle frequency and a low-frequency nerve. Now, as you can imagine, our own ear has about 4,000 inner hair cells, each of which acts as its own independent frequency channel. The cochlear implant, the best cochlear implants that we have, only have roughly 20 channels. And so if you can imagine, that makes the sound very different. And this is a simulation of what speech sounds like through a 20-channel cochlear implant.
Cochlear implants are now in use by nearly 500,000 people worldwide.
So you'll notice this sounds weird, but you can probably understand what that speech says. So compare it to the original. Cochlear implants are now in use by nearly 500,000 people worldwide. Now, cochlear implant users, particularly those that were implanted very young as babies, actually do a lot better on these listening tasks than we do with the simulated cochlear implant sound. And this is really a testament to the brain's ability to take this tonotopically organized information, even really degraded information, and to be able to perceive it as meaningful speech. As we move into the future, we hope to improve on cochlear implant design, on oral habilitation strategies to help cochlear implant users use that sound, and ultimately to actually develop biological therapies to help restore hair cells and more normal, natural acoustic hearing. If you'd like to learn any more about any of these efforts or to talk more about hearing or deafness, please feel free to contact me. Thank you for listening. Will hopefully help us with